Hello, welcome back to class, y'all. Most of my technical issues seem to be resolved, so hopefully I can be getting these videos rolling out to you a little more regularly. Anyway, I want to finish section 3.2 since we didn't quite get around to that, but first let's recap everything we've learned so far. So, computing determinants, that was the previous section. Let's just do one of those really quick. So here's an example. Now say I want the determinant of A. So I want the determinant of this matrix here. Let's see if I can drag that down. Yeah. So now I may look at this and say, ooh, I like that this row has a 0 in it right here. So I'm going to expand along the first row and say, okay, expanding along the first row, remember that checkerboard pattern. It goes plus, minus, plus. So I might look at that and say, okay, if I'm expanding along the first row, it's going to go plus, minus, plus. So then my answer would be 2 from the first entry. And then the determinant of that submatrix that I get when I cut out that first entry's row and column. So that would be -5, 2, 4, -2. And now it's plus, minus, so we'll get minus -1. Determinant of that submatrix that I get when I cut out -1's row and column. So that would leave 3, 2, 1, -2. And then plus, minus, plus, so we'd get plus 0, that last entry, times the determinant of what's left over when I cut out that row and column, which is just going to be 3, -5, 1, 4. And okay, so that's going to give me here, we've got 2 times, the determinant of that 2 by 2 is -5 times -2 minus 2 times 4. And then we've got minus -1, so just plus 1 times the determinant of that matrix would be 3 times -2 minus 2 times 1. And then that last term, we just have 0 times something, so that would just be plus 0. So bringing that all together, we see that this determinant should be 2 times, let's see, 10 minus 8 plus -3 times 2 would be -6, and then minus 2. And putting all that together, 2 times 2 is 4, minus 6 minus 2 would be -4. So let's remember that that's what the answer should come out as. Now, in section 3.2, we talked about a lot of the properties of determinants and some useful things we can do. So let's recap what those were. The big important ones that we had were that row operations change the determinant in certain ways. So the legal row operations that we use when we do row reductions behave quite nicely. So first one was that adding a multiple of one row to another does not change the determinant. Sorry for my handwriting there. The second one was scaling a row. Scaling a row scales the determinant by the same number. And then finally, switching 2 rows. Multiplies the determinant by -1 or negates the determinant, however you want to say that. So let's say negates the determinant. So what that lets us do is that we can perform row operations and know how our determinant's changing as we go along. So let's see an example of that happen. Okay, so back to our example. Say I want the determinant of this now. Then what I can do is, if I look at this, one thing we proved before was that if a matrix is triangular, so everything, so maybe there's some stuff down here, everything either above the diagonal is 0, or alternatively, if everything below the diagonal is 0, with whatever going on up here, then my determinant is just multiply those entries down the diagonal. And so if I look at this, I may see that, oh, I can probably get it to be what we would call lower triangular, get zeros above, fairly easily with some of these row operations. So I could just as easily say, oh, well, if I was to add, say, row 3 to row 2, I know that that doesn't change the determinant, and so the determinant of this original matrix should equal the determinant of the matrix when I add row 3 to row 2. So that would be 4, -1, 0, and then my last row is the same. And then, of course, now I can see that I can get a 0 right here by add, let's say, negative row 2 to row 1. And now I'm just adding a multiple of one row to another, so again, that won't change the determinant. And so I can see that this would still just equal the determinant of, now we're subtracting row 2 from row 1, so I'd have -2, 0, 0, other rows the same. And so the determinant is -2 times -1 times -2, which is -4. Now, some other properties of determinants that were useful. First one I want to mention was that the determinant of a transpose is no different than the determinant of the original matrix. And so what that means is that the way our row operations change a determinant, we can actually use column operations. If all I care about is computing a determinant, I can do the same things with row operations. I can actually do them with column operations, and the effect on the determinant will be the same, which can be pretty useful. So I wanted to repeat that. Another fact that we talked about before was that a matrix is invertible let's say precisely when its determinant is not 0. So why is that? Well, let's think about that a little bit. We know from before that a matrix is invertible. That's equivalent to saying that matrix row reduces to the identity matrix. And the determinant of the identity matrix would just be multiply that diagonal of 1s. So what can we do? I can perform the row operations in reverse, and then I would have this determinant of the identity matrix, and then every time I add a multiple of one row to another, I wouldn't change the determinant. Every time I switch rows, I would get maybe some negatives popping out. And every time I scale a row, I would just take that same scalar and multiply it on. And we can't scale a row by 0, we scale by non-zero numbers. So all these numbers I would end up getting are not 0. So that means that A's determinant would not be 0. So putting all that together, that tells me that A's determinant is not 0. So indeed, these are equivalent. Very useful. Another handy fact that I wanted to point out was that determinant actually splits over multiplication of matrices. This is also very handy. You can get this fact from the same idea. Think in terms of row reductions. The way matrix multiplication works is that if I have, say, some matrices A and B and I'm multiplying them, first off, if either is not invertible, that would imply that the product is not invertible. So the only way the determinant of the product would equal 0 is if one of these equals 0. And now, if I know these matrices are invertible, then I can think about doing some row operations. Right? The matrix A just performs some row or column operations on B, so I can think of undoing that with some reduction to get to the matrix that doesn't have A multiplied on it, and then do some more reduction to get that down to the identity. More reduction. And then perform all those steps in reverse, and then what do I get? I get a string of row reduction steps that take me from I to B. The determinant of the identity matrix is just 1, and then I would have whatever string of numbers pops up in order to get it to determinant of B. So we have some numbers here, negatives for row switches, whatever numbers for scaling, and then I would go up, and then when I perform my operations to go from B back to AB, I would get some other string and then this would be precisely the operations that get me from the identity to B, so that's determinant of B, and then these would be precisely the same row operations. If they take me from B to AB, they would be the ones that take me from the identity to A, so this string would have to be determinant of A, and we get this fact. Now, knowing that the determinant splits over matrix multiplication like this, gives us other handy facts. So for instance, the determinant of an inverse would have to be 1 over the determinant of the original matrix. So why is that? Well, a matrix times its inverse. Well, we know from the fact that the determinant splits over the multiplication that that has to equal the determinant of the inverse times the determinant of A. But also, this is the determinant of the identity. So what's the determinant of the identity? Well, that's 1. And so here we go. So anyway, that was a bit messy and a bit quick, but I just wanted to give a recap. Thank y'all.